The next topic that I would like to cover in this module is going to be focused on potential energy, and I also will be doing some practice problems dealing with how you can calculate or be asked problems about potential energy that you could possibly see on the quiz and test. All right, so the first thing that The first thing I want to do is talk about the definition and kind of what potential energy is. So it's stored energy is also called potential energy, and there are two types of potential energy, and both are considered types of mechanical energy, which falls into the mechanical energy module. The first one is gravitational potential energy, which is the energy due to the height of an object above an arbitrary zero height. Typically, the arbitrary zero height is ground, so the further an object is, the higher the potential energy would be. We also have spring potential energy, which is energy stored in a spring due to its compression or extension. So the stored energy is directly related to the work being done on the object. So just remember, we just covered what work is and how it's considered within the physics terminology. So if you have not watched that presentation, make sure you take a look at that lesson as well. The work to lift an object directly upward is the weight of the object times the height to which the object is lifted. The formula that we're going to be using is W equals Fx or equals mgy. The change in height must be from a defined point that we give a value of Oj, which is typically, like I said earlier, the ground. But sometimes, depending on the wording of the problem, it can be something else. The symbol for potential energy is always U. And we also use the subscript G to differentiate between the gravitational potential energy from other types, like we were just talking about on the previous slide, the spring potential energy. So you'll see it as U sub G, which is the gravitational potential energy, equals mass times gravity times Y, which is going to be the height of the object. So we're going to jump now into the practice problems for potential energy. My lesson last time, I'm going to change my color. So the first problem is going to state an 8.00 kilogram box is carried up, so we know it's going up 4 flights of stairs, and each is 2.5 meters tall. What is the potential energy stored in the boxes at the top of all the stairs? So again, here is the potential energy formula. We plug in what we know. We're going to be solving for the height. For Y, again, Y is going to be the height. Think about why it's Y. Is because it's the Y direction in a graph, right? We have the Y horizontal direction is X and Y. That's what the Y stands for. Anyways, equals 4 times 2.5. The 4 is because there are 4 flights of stairs, and each flight of stairs is 2.5 meters tall. So that's where we're going to calculate, and we should get Y equals 10.0 meters. Then we're going to add what we know into our formula down here. So we have the gravitational potential energy equals 8, which is going to be the mass given to the problem, times 9.8, which is the gravity constant that we should all know. That's what the G is. Times Y, which we just calculated previously, so that's going to be 10. And if we add all that together into our calculator, we should get 784 joules. Again, the same problem. So an 8.00 kilogram box is carried up 4 flights of stairs, each 2.5 meters tall. If the same box was carried up the same flight of stairs on Mars, what would be the potential energy of the box? The acceleration due to gravity on Mars is 3.73 meters per second squared. So again, now this is going to be our gravitational constant. So same Y from the previous problem that we just saw. So again, that's going to be 10. We plug in what we know. 8 is the mass. The new gravitational on Mars is 3.73 times 10. We plug that into our calculator, and we should get 298 joules. All right, so now we have a second type of problem, and then 3 potential questions that associated with this potential energy problem. So it says a spring expands by 0.0675 meters when a 49.0 Newton weight is placed on it. What is the value of the spring constant? So remember Hooke's law. So we're going to be using the formula F equals Kx. We're going to be solving for that K, which is the spring constant. So we rewrite the formula K equals F divided by X. We plug in what we know. 49 newtons, which is given to us in the problem, divided by the distance, which is also given to us in the problem, 0.0675 meters. We plug that into our calculator and we should get 726 Newton meters. The second part of the problem is asking us how much energy is stored in the spring when it is stretched 0.245 meters. So we're using a different formula, and again, remember U is potential energy. This time the sub S is going to be this potential energy of the spring. So we're going to equals 1/2 kx squared. So we plug in what we know. 1/2 equals 726, which is what we calculated right above in the part A, times the new distance, which is going to be the x part of the problem, which is given to us right above, 0.245 meters. And then don't forget to square. We plug that into our calculator. I don't know why I put an equal sign. It should be US. Get rid of that. Multiplying here. Sorry, guys. Plug in 1/2 times 726 times 0.245 squared, and you should get 21.8 joules. Oh no. I think I hit a button on my pen that forced us out. Hopefully my annotation stayed. Yep, here we go. 21.8 joules. My color. Sorry, guys. Alright, and now finally the last part of this problem says how much does the spring need to be compressed to store 12.0 joules of energy? So again, we can use the same problem, the same formula as before. Again, U is potential energy, the sub S is just talking about the spring potential energy. So same formula, except now we're going to be solving for the distance. So we're going to be solving for that X part of the component. So we rewrite the equation. Remember that in order to do the reverse of a square, we're going to square root the whole side. We plug in what we know. So we have X equals the square root of 2 times 12, and the 12 is coming from the problem right here, divided by 726. Again, the 726 came from the first part of part A of the problem. We plug that into our calculators and we should get 0.182 meters. And that is it for the potential energy section of this lesson. Let me know if you have any questions. Thanks for watching.